Okay, so the first thing you want to do, you can either use the GeoBoard, because we're going to be talking about area. So you can use the GeoPaper. This is a GeoPaper, it's a grid. You also have more GeoPaper on the back on, let me see if I can find the page. On page 217 and 219, you have more paper. So if at any point on this chapter you need some paper to draw, you can do it in there, okay? So, um, so you can use also the following website. It's an application. So let's go apps.mathlearningcenter.org/geoboard backslash. And then what that does, I'm going to show you quickly because I'm still going to use the one on your workbook. But what that does basically is give you the same type of grid as we had in same type of grid that we had in in the book on page 145, because it's a geodot that has a 5x5. So, and this is just like that 5x5. And then these are formed like using rubber bands. For example, in this first activity that you have on page 145, it says that you want to create um, a not a rectangular, a polygon, and try to make it as big as the wide of the figure. See right here? So I'm going to do this, and then I'm going to do over here, and then I'm going to do this right here, maybe right there. Okay. So do the figure as however you want, right? And then, but the thing is that whatever figure you create in there, you're going to write it on both because we're going to do the same thing. We're going to try to find the area. That's what we're doing. We're trying to find the area of this polygon in two different ways, in two different methods. And those are the methods that are going to be described in your figure. So actually, I am going to do, let me see if I can draw this one in here. So I am going to draw this in my paper, and then you guys create whichever one you want. You don't have to do the same one. But that figure that I have there, let me show you as I'm building it. Let me share my new screen. And right, so I'm going to try to create that image that I had before. So I went from the top here to the second down here. And these should be straight lines, not curves, okay? And then from there, I went over here. And yes, I should have told you, you need to have a ruler or something which you can make straight edge and measure, because in this segment, we are going to measure a few things. So you do need a ruler. Okay, and then we're going to go to the second one here. And then straight up. And then to the top. Okay, and then whatever figure you did here, you're going to copy it exactly on the other side. Because we're going to do, we are going to do both with two different methods. One of the methods that we're going to do first is with the addition method. Okay, and the other one is going to be with a rectangular method. Okay, so those are the two methods we're going to do. So I'm going to do this first one with the addition method. Okay, and then I'm going to do this one with the rectangular method. So let me quickly draw the same one that I just drew here. Mm. 3, go up, and go to the corner, and then go to the second one down. Okay, so there you go, exactly the same figure, and then we're going to do it two different methods, okay? So the first method, if you read up here, it says that, let me make it this a little bigger, right? We say that when you connect 4 dots this way, that area inside is going to be called as 1 unit squared, okay? So we are going to, again, like I said, this is about area, finding the area. And so yeah, so we are going to try to find the area of this particular figure, or at least mine. You can find yours wherever where you are. Okay, so for the addition method, the goal is to form those rectangles. So we are going to draw right? Unit squares. The thing is that I cannot form a unit square up here, see? Because that is outside the thing. So I cannot form a unit square, but you can most definitely do this, okay? And you can join this one up here like that. And then you can join this one up here, this one down here, and then you can join this one down here, and then we can join this one, we can join that one, and we can join this. Now, one of the things I want you to be aware, okay, and I'm gonna do it like over here, so I don't use the same space. And let me go ahead and make this bigger. Okay, one of the things I want you to be aware is that this vertically is 1 unit, horizontally is 1 unit, but diagonally, so when you draw this diagonal from here to here, that is not 1 unit. That is actually square root of 2. Okay, why? Because we are actually using Pythagorean theorem to find that length. So the diagonal from 1 to 1 like this is going to be square root of 2. But if you go further up, right, if you go across 2, then as you see, to find this hypotenuse, because that's what it's going to be forming like a right triangle, see? That's why we use Pythagorean theorem. So this is a 2 by 2. So that means that's going to be square root of 2 squared plus 2 squared, right? 2 squared and 2 squared, which is 4 plus 4, which is 16. And then the square root of 16 will be 4. So this is actually 4. See, so you will have to like work backwards with a Pythagorean theorem so you know what is going to be that part of there. And it all depends on the triangle, right? That you form the right triangle. So if you see this right triangle, that's a 1 unit and this is a 2 unit. So basically we're squaring the 2 and we're squaring the 1. And then you get 4 plus 1, which is 5. So that is square root of 5. So this one right here is square root of 5. The hypotenuse. So you see that it depends. It's not going to be 1. It's not going to be 2. You need to be careful when you're going across. Okay, that's only happens when you have the across. Now, having said that, right? I want you to take a look at the figure that you drew. And if you did not make a complicated figure, like me, I made a complicated figure. If you did not make a complicated figure, that's fine. Okay, because then you're going to be able to form nicely numbers. Now, what is the goal here? The goal here is to find how many units squared this figure that you draw is. So I can count. So you see here, this is half and this is half. So we can actually make 1 unit. This 1 unit, this 1 unit, this 1 unit. Now you see here, we got several triangles. We got 1 triangle, 2 triangles, 3 triangles, 4 triangles. And they are kind of weird triangles, right? Because we don't have like the direct height or stuff like that. So what we could do is that we need to find, so this one is not that bad. This is forms a right triangle. So we can actually do a 1 by 2, right? Uh, so that means that we have that the area of the triangle is 1/2 base times height, just like we saw it on the previous chapters. And then we're going to have in there, it's going to be 1/2. The base is 1, right? Because this is 1. And the height is straight 1, 2, because it's perpendicular to the base. And then you're going to see that 2 times 1 times 1 is 2 divided by 2 is 1. So this whole triangle measures 1. Okay. Now, as you see, these other ones are not. Okay, so you see that these other triangles, like this one, and this one, and this one, they are, I want to say abnormal, but they don't have a clear 90-degree angle like that one, right? So this is what we need to do with these triangles. They don't have like a perpendicular base that we can find with the altitude. So let's take a look first at this tiny triangle right here. So the first thing you need to do is I want to draw my height from this vertex. But again, because this is slanted, I cannot draw the perpendicular line to there. So I am going to extend this side, right? And then now you see you have formed a line, and then I'm going to take this vertex because again, I'm going to try to draw the line perpendicular to this side. So from this vertex, I'm going to extend it and I'm going to form a 90-degree angle. So now I have a height because the height has to be perpendicular to the base. Now remember that this right here will be my height because this is only part of this triangle. So this will be 1 and this will be 1. So that means that for the area for this tiny triangle, it will be area of the triangle. It will be 1/2, 1 and 1. 1 from the height because this is the height, and then 1 from the base because this will be the base. Okay, so that means that you get that this little piece right here, because 1 times 1 times 1 divided by 2 is 0.5, right? So this is going to be 0.5 or 1/2. Okay, then we're going to do the same thing with the big triangle right here. Again, I want to draw from this vertex down my perpendicular line so I can do the area, the height. But again, I cannot draw a perpendicular to here, so I'm going to extend this side, and you see how I form a 90-degree angle there? So now I'm going to count. So my base is 1, because this is my base 1. But then I have 1, 2, 3 as my height. So the area of this triangle is going to be 1/2 the base of 1 times the height of 3. So that will be 3.5, or 3/2, and that it will be 1.5, or 1.5. Okay, so this is 1 and 1/2. And then the last one is this one right here. Again, same story. I'm going to extend this height all the way down so I can make a perpendicular. And then see, I'm going to do a perpendicular to this base. So now I had a base of 1 and a height of 1, 2, 3. So it's just like this one right here. So this has area of this triangle. This one have a base of 1 and a height of 3. So again, this is going to be 3/2, which is 1 and 1/2. So this is also 1 and 1/2. And now we need to accumulate, because that's what is called the addition method. You are going to add all those tiny pieces so you figure out what it is. Okay, so we have 1 and 1/2, or 1.5. Let's do the decimal because I know you guys like the decimal. And another 1.5. And then we got a 0.5. So these are the three-way triangles. And then we have half and half, so 0.5 and 0.5. And then we have 1, 2, 3, 4. And then we have 4. I'm going to put it up here. So this half and this half makes 1. This half and this half makes 2.5. So I'm going to put the 0.5, carry the 2. And then we got 6, 7, 8. So this figure measures 8.5 units squared. You can write it with that little square right there. Okay. Now, so you see, even though it seems easy, it's all going to depend on your drawing. Okay. See, I did another drawing before, and it wasn't that bad. See, they have nice right triangles. So it was easy to find the area of each one of those triangles, right? So, but when you have more complicated figures like this that has a lot of diagonals, right? Then that's when you have the problem of having to extend and extend, so you'll be able to find the height. Because remember, the height in the triangle is always going to be perpendicular to the base, okay? So now, for this specific case, that's why we have different methods. You need to select, according to your figure, you need to select what method works better for you, okay? So for me, I think this method would have been better, the rectangular method. Now, what is the rectangular method? The rectangular method has a goal of enclosing in a rectangle. Let me see if I can just do this, but let me do a highlighter instead. So in that way, I don't erase the figure. I'm gonna do a highlighter. And the goal here is to have the figure that you drew, have it inside a rectangle or a square in this case, right? Because this is a 5x5. Now, the goal is, you see how you have crisp 90-degree angles, right? And in this case, at least we can draw the height of this triangle right here, and it's 90 degrees. That's a nice one. In here, you form different figures, right? And what we're going to do for this one is that we are going to divide it. Let's see if we can divide it. We can divide it into a small triangle, right? And then a big triangle right here. You see how we did that? Now, the goal is do a subtraction. You're going to find the area of the rectangle, which in this case is a 5x5. So it's going to be 25 units squared. Okay. And then subtract from here all this area. The area that's not supposed to be there, right? Which in this case, for me, I formed three different triangles. One triangle, two triangles, three triangles, four triangles. So I'm going to actually, let me list this and say this is A, this is B, this is C, and this is D. So I'm going to find the area of those four triangles, and then I'm going to subtract it from 25. So let's find the area of A. So A is a 1 by 1, right? So you have 1/2, 1 by 1. So you see it's going to be 0.5, right? Because it's 1/2. Then we have this area. So this is a 2 by 1, 2, 3. So the area of this is B triangle. It's going to be 1/2, 2 by 3. So basically that's 6 divided by 2, which is 3 units. So this is going to be 3 units. And then we're going to do now the area of C. And this is going to be the height, and this is going to be my base. So C triangle is going to be a height of 1 and a base of 1, 2, 3, 4. So basically we're doing 4 divided by 2, which is 2. And then lastly, this big long triangle. So D triangle. And then we are going to have a base of 1 and then a height of 1, 2, 3, 4. So another 2, right? Because 4 divided by 2 is 2. So we're going to add this. 2 plus 2 is 4. 4 plus 3 is 7.5. So we're going to subtract from here 7.5. And let's see what do we get. Let's see, we get half. And then this will be a 4. That's why 14. So we are going to borrow. Let's see. So this is 7.5. Let's see. Let's see. Okay, I realized I did a typo. This is not a 5 by 5. This is a 4. See, 1, 2, 3, 4 by 1, 2, 3, 4. So I apologize about that. This is supposed to be a 4 by 4, which is 16. And then we're going to subtract the 7.5 from 16. And that's where you get your 8.5. So you see that now the 8.5 matches the 8.5 that we got here. See? Now, for this one, obviously, this one will have, took me less time to be able to complete this one than I did last one, because I had to extend on the previous one, I had to extend the sides to be able to get a 90-degree angle and then be able to find the formula for the triangle and subtract. So the reason we give you two different options is for you to choose accordingly. Okay. So it says, which of the two methods you find appropriate for the figure you found? For me, I would say that the rectangular method, because my figure has a lot of irregular shapes. But, for example, this one, I would have rather used that one because this was really easy to add than trying to find the heights, even though this is not complicated either. But for this figure specifically, I would have done the addition method. But for the one that I have here, definitely I would do the rectangular method because my figure, see, has a very irregular shape. So it's hard kind of to determine what shape you have. I hope that makes sense, okay? So that's why on the back, the practice problems that you have on the back, you needed to find the area of all these figures right here. And as you see, you have some that are really easy. And so for example, for this one, I would use the addition method because this is 1.5, so this is 1.5. You see how fast that was? Okay. But for things that have diagonals like this one, for that, it's better to use the rectangular method. So for this one, I'm actually going to enclose this in a rectangle. See, and I have half here and I have another half here. And then I'm going to throw here to have a thing, and I have half and half. So that's actually 1. So this is 1/2 and this is 1/2. So I have 2. So I'm going to subtract from 2. So this is a 2 by 2, right? So I'm going to subtract from 4, 2. So that means I might have 2 units. So this is 2 units squared. See? So you're going to have very weird shapes like this one, see? This one is better to do the rectangular method. So, and then this one too, because again, there is no perpendicular side. So for this one, I will also do the rectangular method. But for E, you can draw directly. So you see the dot right here? So we can draw the height. So this one is just straightforward applying the triangle area, right? So if you have a base of 1, 2, 3, 4, 5, 6, right, times 1/2 times the height, which is 1, 2, 3, 4, right? So you have 24 divided by 2, which is 12. So E is 12. See? Same thing for this one. This one you don't even have to do anything. You have a right angle right there. So this is a 2 by 1, 2, 3, 4, 5. So, but for this one right here, this is really hard to do just by that. So this one I will have to enclose in the rectangle. In the rectangle for this one is ginormous. See? That's the ginormous rectangle. And then I have this triangle right here, all this area. And then this triangle right here. Secant doesn't go all the way to the corner, so be careful. Those are your two right triangles. So for that, I am going to do, this is a 1, 2, 3, 4, 5, 6, 7, 8 by 1, 2, 3, 4, 5. So 5 times 8 is 40 divided by 2. This is 20. And then this one is a 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A 10 by 1, 2, 3, 4, 5. So this is 50 divided by 2, which is 25. And then we have 25 plus 20, which is 45, which I'm going to subtract from. We said that this was a 5, this was a 5 by 10. So that will be 50. So 50 minus 45 is 5. So this triangle is 5 units squared. Okay. So again, on some occasion, it's better to use the rectangular method, and some other occasion, it's better to use just the addition method. Okay, like this one. You can do this one with the addition method. You can do this one with the addition method. You can do that one with the addition method. Right? So there's so many that you can do with the addition method. But for the purposes of that you need to be able to know both methods and explain, just like I put here in the front, why the other method is better. Okay, whether you selected that method. Okay, just to give you, let me see if I can show you the whole thing. So you can grade your paper. Again, and you can go ahead and pause if you want, and then draw it and then check your work. Okay, so that is the answers for that. So you see some I did with the addition method, and some I went ahead and I did the rectangular method. Okay. He says, do you think the shape of the figures make a difference in which method is easier to use? Approximately, obviously, yes, right? We just said that. Okay, next. For this part, we are going to understand the area formula. So how is it come that you can always, you have to memorize all these formulas? Well, you don't have to if you understand them, right? So if we are base our information on the rectangle area, right? We know that the rectangle is just the length times the width. So we can try to have all the figures that we have, at least all the quadrilaterals, and even the triangles. We're going to try to see if we can form a rectangle and then derive from the rectangle formula the other formulas. So for example, this is a parallelogram. A is a parallelogram. So if I draw right here, right, a straight line, and then I take this piece right here and I move it, I translate it over here. See, I put this piece right here. What do you form now? A rectangle, right? So but you see that this right here, this is what we call the height, and then this is what we call the base. So that's why the area of a parallelogram is base times height, which is the same thing as length times width in the rectangle. And the same thing could be applied to this one, right? If you draw right here, and then you're going to see that's the same piece you're missing over here, right? You're going to take this, and you're going to move it over here. Now you have a rectangle. So again, that's why you have length, base times height in there. And that's why the area of the parallelogram is derived from length times width, and now the length is going to be your base times the width, that's just going to be the height. And then you have the little figure. And still the height is always going to be perpendicular to the base. So this is going to be the height, and this is going to be your base. Okay? Now, let's take a look at, and again, if you need more time to write, just pause the video and you should be able to continue. Okay, well, let's take a look at the area of a triangle. And I give you two type of triangles, right? I give you a right triangle, and I give you a obtuse triangle. So what are we going to do? We are going to try to create a rectangle. And this is pretty easy done, right? Right here. Then I'm going to find the length and the width. So this is a 1, 2, 3, 4. So this is 4 by 1, 2, 3, 4, 5, 6. So I can do that the area of the triangle is going to be what? It's going to be 6 times 4, right? If I do base times width. But what happened? I originally did not have two congruent triangles. I only had one. That's why we divide by 2. That's why we multiply by that 1/2. So we're going to have what? 24 divided by 2, which is 12 units squared. Right? So that's why. And the same thing here. In here, we can actually form a parallelogram, right? Since we already know how to derive the parallelogram. And then we have, let's see, 1, 2, 3, 4, 5. And we're going to do from here, we're going to do 2, 3, 4, 5. Yeah. And then we're going to draw, right there. And then if we draw again the altitude or the height is always perpendicular to the base. So this is your height and this is your base from here to here. Okay, so the height is 1, 2, 3, 4. And then the base is 1, 2, 3, 4, 5, 6, 7, 8. But again, I did not start it with a parallelogram. I started with a triangle, which is half the size. So that's what we're going to divide by 2. So that's 32 divided by 2, which is 16. 16 units square. Okay, so as you see, right, the area of a triangle is going to be base times height divided by 2, which can also write as 1/2 base times the height. Okay, and that's because we only use half of the area of the rectangle or parallelogram. right? And similarly, you are going to do the trapezoid. This is important because one of these developing is not that you're going to, I did put it that you're going to explain it on your homework. So you have to explain, one I put in the homework is the trapezoid. So pay closer, whatever we do right now, that's exactly what you're going to do on your homework, okay? So let me see. I think I put the homework away, but let me see if I can find the homework quickly. And give me 1 second. Let me see. Yes, see homework 6. On homework 6, problem number 3, it says explain and illustrate how to use the area of the parallelogram to come up with the area of the trapezoid. Okay, so again, so for that one, we are going to, I think it's very similar to this one, but it doesn't matter. So you're going to say, well, what are you going to do? You're going to take this exact trapezoid and you're basically kind of going to flip it over. And you're going to, when you flip it over, you're going to create a parallelogram. So this is 1, 2, and this is 1, 2, 3, 4, 5, 6. Okay. So step 1 basically is you're going to copy the trapezoid given, and then you're going to flip it. So you form a parallelogram. 1, 2, 3, 4, 5, 6, 1, 2. And then you're going to connect those dots. So as you see, this is this one flipped over. Okay. Because now I have 6 here on the top and I have 2 here on the bottom. Okay, the next step is now we're going to apply the parallelogram, right? So remember that this is actually, this little piece is B1 and this little piece is B2. And here I have B1 and here I have B2, okay? So to be able to find the, so, basically either one of these two sides, right? Which is going to be the basis, the base of the parallelogram is going to measure 8, right? Because this is 6 plus 2. So what we're doing is B1 plus B2 is going to give you what we're going to call B, okay? This is what we're going to call B. And then the height, remember the height is perpendicular. So we are going just to draw it. And then this is a 1, 2, 3, 4. So the height is 4. So we're going to find the area of the parallelogram, which is base times height, which is what? 8 times 4. But remember that we did not start it with a parallelogram. We started with a trapezoid and we double it, right? We double it. So to find the area of the trapezoid, we are going to do base times height, but we're going to divide it by 2, okay? Now, we don't have just one base. We have what? 2 bases. Remember what B? We call B1 plus B2. So we're going to substitute that B1 plus B2 times H divided by 2. And that is the formula for the area of the trapezoid. Okay? And if you're going to see, this is exactly the same thing. If you copy this and flip it to the other side, right? So you rotate it this way, you're going to end with a rectangle. And using the rectangle, then again, the area of the rectangle will be length times width, right? But it's the same story. So this one has what, 2 here? And this one has 1, 2, 3, 4, 5, 6, 7. So now I'm going to have 1, 2, 3, 4, 5, 6, 7. And then this is 1, 2. See? So again, that's, you need to have the illustration and the explanation of what we just said for that part. And then the next one is the kite. In the kite, the diagonals cut the kite into 4 pieces. These 2 triangles are congruent and these 2 triangles are congruent, okay? So this is what we're going to do. We are going to draw this diagonal in these 2 triangles, okay? This is a 1, 2, 3, 4, 5, 6, 7. So we're going to do 1, 2, 3, 4, 5, 6, 7. Then I am going to draw, this is a 2 by 2. So I'm going to draw that one. And then this one right here. And this is 2 and that's 1, okay? Then this is what is going to happen. I'm going to take this triangle 4 and I'm going to put it up here. I'm so sorry, my dog is snoring. And I'm going to put this triangle 3 up here, and that's going to be a rectangle. See, I took my kite, I cut it into 4 triangles, and I made a rectangle. And now I'm going to use, you need to be careful because we were using diagonals, right? So this is diagonal 1, so I'm going to call it D1. And this piece plus that piece is diagonal 2. And now what happened? I'm only using this tiny piece right here. So the height is actually half of diagonal 2. You see, it was cut in half. So now to find the area, so let's put area of the rectangle first. It's going to be base times height or length times width. And that's going to be D1 times D2 divided by 2, right? That's what I get from the area of the rectangle. Then I'm going to convert it. The area of the kite is going to be, basically, we're going to combine those two. D1 times D2 divided by 2, or we can also say 1/2 D1 times D2. So basically, you are going to multiply the two diagonals, and then you're going to divide it in half, okay? And then, very similar, I understand that circles are not polygons, right? Because they're made of curves, not straight line. But we can approximate the perimeter, right, which is the circumference of the, and find the area also of the circle by trying to convert it also into a parallelogram, right? This looks like a parallelogram except for the hump that they have on the bottom and the top, but they use it. Now remember something, that circles, we use some approximation. What is the approximation? The approximation is pi, right? We use pi as an approximation, so you're never going to have an exact answer. We always approximate when we're trying to find area of circles and perimeter or circumference of circles, okay? So let me write down the formula for circumference, right? Circumference, which is like perimeter, and it's 2 pi r, okay? So why we need to use perimeter? Because what do you think are these humps right here on the top and these humps right here on the bottom? Those are the curves. See these curves? These curves are those little humps, okay? And since we're using the whole thing, the whole perimeter or circumference of the circle, we're going to have to use it, okay? Now remember that if we were to find the area of the parallelogram, we need a height, and then we need a width, or the length, right, or the base. We need the base. So the base, this part of the base, is going to be half of the circumference. Because you see, you have only half. See, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, you have half of the circle in those 10 little humps. So that means you have half of the circumference. So your base is going to be 2 pi r divided by 2, because it's half. Now what happens with this 2 and that 2? They cancel and you just get pi r. The height, if you see, is the radius of the circle. So we can approximate it, and we can say approximation. We can say that the radius is approximate, the height is going to be approximate the radius of the circle, because this is r, okay? So now I can actually form, right? I can actually form the area. It says, how does the base length of the parallelogram related to the circumference of the circle? We're going to put here that the base length is half the circumference. And how is the height of the parallelogram related to the radius? Oh, we just did that. The radius is an approximation, or the height is or the radius is an approximation of the height. Right? So now we're gonna go from area of the parallelogram into area of the circle. So we're gonna have base times height, which is pi r. Remember, that's what we said it was, base times the height, and we said that the height is going to be an approximation of r. So we end with pi r squared, and that is the area of the circle, is pi r squared. So you see that when you understand area of a rectangle in parallelogram, then you should be able to derive all the other formulas. So you don't have to memorize it. You can actually derive it, okay? Now, for this part, we're going to try to do something similar to what we've been doing. But in this case, these are regular polygons. Okay, so that's what we're looking to find. We're finding the area of regular polygons. Why is that important? Why isn't just telling you polygons? Because remember that a regular polygon, all the sides measure the same and all the angles measure the same. So if I have a polygon, just like I did down here, right? I have a octagon. I went ahead and I drew all my diagonals. and I saw that I formed 8 little triangles, right? I know that if I find the area of one of these little triangles and multiply by the number of sides that the polygon has, that's going to give me the area of that polygon, okay? Makes sense, right? Now, one of the things, this right here, this is called A. A because it's the height of the little triangle, but we don't call it height. We call it apothem because it's basically the height of this tiny little piece that is a triangle. Okay, so see right here too, that's the apothem, and it's always perpendicular to the base, which is the side, and then of course, right, it is going to be that apothem as you see there is going to be the same thing um, with that. It's always going to be perpendicular to the base because it's got kind of the area of the triangle, right? Base times the height divided by 2. So let's see how we can derive from this octagon. We can derive the generic formula. So they tell me that this is S. What does that mean? And you see these little ticks because again, we have a regular octagon. So this means it's going to be S, that's going to be S, it's 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 going to be S. And all of the sides are going to be S, right? So it says, so we start with drawing the diagonals. We already did it. We label each side S, which we already did. We're going to label the apothem, which is the height of the triangle. See, I did already. And then we're going to find the area of that little triangle. So this is what we need to do. So the area of the little triangle is going to be the base, which is S, times the height, which is A, divided by 2, right? Then the next step is to write the perimeter of the octagon in this case, right? The regular octagon. So perimeter is just the sum of the sides of the measurement of the sides of the octagon. So since we have 8 congruent sides that measure S, then that means here that the perimeter is going to be 8S. Now use all the information gathered above and write the formula for area of the octagon. So we're going to say that area of the regular octagon is going to be equal to 8, right? The number of sides, because we have also what? 8 little triangles, right? Times the area of that little triangle, which is side times A divided by 2, right? Because that's what we agreed. And then what happens here? We can actually divide A divided by 2, which is 4. So you get 4 times S times A. So what are we going to do? We need to derive from this formula that we just did, we need to derive the formula for any regular polygon, okay? Any regular polygon. So we're going to call the side of any regular polygon N. Area of any regular n-sided polygon. See, that's what I put the n, so we can just n-side it. So that's going to be equal to, remember, 8 was n, times the sides of this, we can rewrite the same way. Sides times A divided by 2. Which again, we are going to just, since everything is multiplication, I'm just going to put n times S times A divided by 2. Okay? And then we have, you notice something, right? Look up here. 8 is representing n, right? And S is going to representing that, and that's representing what? Perimeter. So we can say that P, this is perimeter, that P times A divided by 2 is the area of any regular polygon. Okay? Okay. So since we're talking about area and we're talking about the grid paper and such, I'm sorry, we are going to use the grid paper and then don't draw diagonal triangles. We're going to draw a vertical horizontal so we can have a right angle and we know exactly what is the length of the sides. So one of the sides is going to measure 3. So I'm going to put the side that measures 3 right here. 1, 2, 3. See, 1, 2, 3. This measures 3. Then I'm going to put another side that measures 4 right here. 1, 2, 3, 4. And then the diagonal that connects it is going to be the hypotenuse that is going to measure 5. And I don't think I have, let me see. This is like half a centimeter. So we got 1, 2, 3, 4, 5. See, so that's right there because each one of these things, see, is half a centimeter, not a whole full centimeter. Anyway, now, so we know that this is 5. Now, the next step is to create a square, not a rectangle, a square for each one of these sides. So if this is 3, then this is also going to be 3 here. 1, 2, 3. See, and you're going to form an area there, which this is an, let's say this is A and that's A, so that is A squared. In this case, it's 9, right? Over here, we're going to do the same thing. If this is 4, then you're going to do 1, 2, 3, 4. And that's 4, 2, so that's 16. We can say this is B, that's B, so this is going to be B squared. And then this one is kind of a little harder, right? Because we're going to go what? 1, 2, 3, 4. 1, 2, 3. So we're going to do 1, 2, 3. And then let's see here. We're going to do 1, 2, 3. And then we're going to connect. And this is going to be, let's see. 1, 2, 3. This is going to be C and C, which is C squared. And this is 5 and 5, so that's 25. Okay. So you can always, I don't think I have it in here. I have the other activity. But if you have grid paper, that's what I said that you could use grid paper. Let me see. And I don't have, and bear with me because I don't have it in here. But I'm going to do A, 1, 2, 3, 1, 2, 3. This is 9 units. And then I'm going to do 1, 2, 3, 4, 1, 2, 3, 4. And then 16 units squared. And then we're going to do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you're going to make 25 units square. Okay. Then I wanted to show you here. So I did it on grid paper because this is easier to draw and cut fast. So I'm going to cut it. And you can do this at home too. This is kind of a good activity for your students also to come up with the Pythagorean theorem. So I'm going to do okay, so that is my 3 pieces, right? So I am going to place my 9 units squared inside my 25. And then I'm going to take my 16 and I'm going to cut it. And I'm going to put 2 columns right there. And then put six over here. And the last 2 that will go down here. And again, you can do this. You can ask your students, you can give your student grid paper, or you can use it on the computer because there are some other softwares that they can do also as well, right? But you see that, yes, you have to cut it, but you're going to see that you do form exactly 25 unit squares. So what we just did? What we just did was saying that, again, when you have a side or a leg of a right triangle and you square it, and you add the square of the second side, you are going to get the squared of the third side, okay? So this is 9 plus 16 is equal to 25. So you end with 25 is equal to 25, see? And this is true because this is, again, the Pythagorean theorem. You have a squared plus b squared is equal to c squared, right? And that is the derive of the Pythagorean theorem that you did in there. So on the back, Let me just move this little pieces. Now, on the back, you have, let me just put those pieces in. You have application problem. You see right here, this is the little thing. It says a square with side A. It was 9 units squared. Square with side B was 16 units squared. And area of side C was 25 units squared, right? Using just you, so it was just you. And then can you find the relationship? And that's what the student can come up with as the sum of the squares of the two sides or legs, right? Of a right triangle are equal to the square of the hypotenuse. And then let's say, can you prove the conjecture geometrically? And that's what I did right here, right? So this one I kind of taped it. But yeah, see, this right here is the little 9, 3 by 3. And then the 16, I cut it first in here. 1, 2, 3, 4, 5, 6, 7, 8. Then I do the other one. 9, 10, 11, 12, 13, 14. And then the two little pieces, 15, 16. Right? And that's how we came up with the Pythagorean theorem. Now, all of these that are in this page is in the next page on the top. They're just application problems, okay, for Pythagorean theorem. So when you buy a TV, all those rectangular TVs basically tells you the distance of the diagonal, okay? And the distance from the diagonal, uh, it's a rectangular, right? It's a rectangular screen. So we can find, if we have the two length and width of the screen, then we can find the diagonal. And that's what we did here. So we got the one side was 39 inches, the other side was 52 inches. So once we substitute and square it, we're going to get 4,225. Now be aware that what they're giving you is the squared of the hypotenuse, right? So if I draw it over here, the square of the hypotenuse. So how can I find the leg? By basically measuring, right? By basically measuring the sides, right? So what two sides, because you're multiplied by the same number, what two sides uh, that is the same number multiplied by itself. One side multiplied by itself give you 4,225, and that would be 65. So how do I get from here to here? By finding the square root, which is the inverse operation of squaring a number, okay? And that's how we got the 65. And then on the next page, again, you got two more. We're always going to assume that any building standing is perpendicular to the ground, or any flagpole standing is perpendicular to the ground, right? So again, that's why we create right triangles, because this is important. You cannot use the Pythagorean theorem unless you have a right triangle. If you don't have a right triangle, you cannot use the Pythagorean theorem. Okay, hopefully that makes sense. And you have, um, in this case, I have that hypotenuse and a leg. I'm missing another leg. So once you substitute, you see that when you're finding a leg, it doesn't matter if it's A or B, but when you're finding a leg, you actually ending subtracting the other leg from the hypotenuse. So when you're trying to find a leg, you are going to subtract the square of the leg given from the square of the hypotenuse. And then you apply the square root to whatever the difference is left, and that's going to give you the side that you're missing. Okay. Um, and then we do have some special triangles that I give you over here. This is just kind of a definition, so there's nothing basically to do here. The application is on the back. So they tell you that there's a special type of right triangle. Pythagorean theorem applies to any right triangle. Doesn't have to be special. As long as it's right, it works. But this one, you don't even have to do work. You can do it right away if you want to memorize these two. And for these, you're going to need the measurement of the sides or the measurement of the angle. So this one is saying that this is 45, 45, and 90. So that means that this is a isosceles triangle, see? Because the opposite sides of the congruent angles are congruent. So to find if you square this one, right? If you square S and you square S, you're going to get 2S squared, right? So you have S and you square, and you have another S and you square it. And now we're trying to find C squared, right? So you're going to end with 2S squared. And if you apply square root, the S goes outside, but the 2 stays inside because the 2 is not a perfect square. But S was S squared, see? That's why it came outside. So that's what they got. That's when you have a right isosceles triangle. And then when you have a triangle that the angles are 30, 60, 90, see 30, 60, 90, then on those triangles, you're going to have a short side, see, S for short. Then you're going to have a long side. This is the long. And then you're going to have the hypotenuse. Okay. And a special relationship happens. So if the small side is S, then the long side is whatever the short side is times 3 square root of 3. And the hypotenuse is going to be twice the short side. Okay. Again, all that is given in here already. Then again, some application problems from using those rules. So we have here, this is 90, that's 30. So even though they did not give me the 60, I can find it. I have 90 and 30, so I can find that this is 60. So I have a 30, 60, 90. And they say that this side is 6 feet. And it says, how far is the ramp from the platform? And how long is the ramp from the top of the platform? So again, if I have 6, and you see that 6 is opposite to the smaller angle, 30, that means that's a small side. So the long side is going to be 6 times square root of 3, and the hypotenuse is going to be twice the short side. Okay. And again, all of these are applications of those. And this one, you see that you have a isosceles triangle. So it's going to be whatever this is times square root of 2. And then over here you have 45, 45. So you have a isosceles. So you're going to have the, you can find this right here. So this is, in this case, you have the height, and then we need to find the base. But to be able to find the base, you need to find what that little piece is, right? So we are going to solve the equation. So this is going to be the long side, which is of the 90 degree, which means that's the hypotenuse. And whatever the leg is going to be that times square root of 2. But if we need to find this tiny piece right here, because we need to be able to find the height as well, then that means that we need to divide this by 2. But you're dividing it by 2, not by square root of 2. So that means when you divide this by 2, you're going to end with 12 and square root of 2 and 12 square root of 2. Okay, so and that's we're asking for the height, because the height is also going to be perpendicular, and it's also going to be the same measurement as this one. So that means that you're going to end with another tiny isosceles triangle. Okay. Okay. Then we have the distance formula. I am not going to go over all the problems, but I am going to give you, so you need to find like the coordinates of A and B. Let's say I'm going to do the first one. The first one, this is segment 1 right here, A and B. So you're going to identify the order pair for A and the order pair for B. Order pair for A is 1, 2. Order pair for B is 5, 2. To find the midpoint is basically the average of the two segments. Okay, that's what you're doing, the average of the two segments. So basically, you're going to count is what 1, 2, 3, 4. So it's going to be like right there in the middle, right? And what is that point? That point is 1, 2, 3 by 1, 2. So this is 3, 2, right? So you can actually find the midpoint. Now, is there a formula? Yes, there is a formula. Like I said, it's the average of the x's, right? Divide and the average of the x's. In other words, you have two x's, so you're going to divide by 2 after you add it, and then you're going to add the two y's and divide by 2, and that's going to give you the coordinate of the midpoint. So let me give you these answers. Again, you can pause if you want to and copy it, and that way you have it. And I'll apologize ahead of time, but yes, this chapter or this video may be a little long because there's a lot of material in this chapter. Okay. And there are a lot of applications for midpoint. And you say, oh, when am I going to use this? Well, for the midpoint, for example, on the next page, you have a, not this one, sorry. You have, where's my application file? Oh, no, you do have it. Okay, it is here. You have the distance formula. So the distance formula is different from the midpoint formula. We are going to practice those in a minute, okay? We application problems. But the distance formula is kind of derived from the Pythagorean theorem. So basically, instead of giving you a right triangle and giving you the legs of the right triangle, I'm just going to give you the coordinates of A and the coordinates of B. Okay. So, but we can always find the change in the Y's and the change in the X by doing the differences. Now, for this case, what if I don't give you the grid? Instead of you trying to draw it on the grid, you are going to use whatever the coordinates are for A and B in this case. Okay. So in this case, right? I have what? I have 1, 2, 3, 4, 5, 6, 7, right? And then hold on. They give you the information. So it says that AC is 9 and a CB is 12. Obviously, this is not drawn to scale, but so we're going to put it in here, square it, and then to be able to find AB, you're going to have to find the square root of 225, which is 15. Now, what if I don't give you the grid and I just give you the order pairs? Then you're going to label it. It's important that you label, right? So the distance formula have the difference in the x's. So you have like x2 minus x1, and then like right here, see, and then you square it, plus the difference in the y, see that it's always minus. So if you have a negative, be careful with those. And then you're going to square it. So before you can get it out, you needed to add it or subtract it, and then you're going to square it. And once you square it, you said that you got 15. So the regular formula for the distance formula is this, and then which is kind of derived from the Pythagorean theorem, see? So instead of having x2 minus x1, we have a, and then instead of having y2 minus y1, we just have b. But it's the same thing. Again, you can pause and copy, right? Then we have the application problems. And some are easier than others, right? So this is finding midpoint. So you need to find midpoints between the different segments. So you have like your X and your Y and the order pairs. See, I wrote the order pairs in here. So yeah. And then this is I'm trying to find this distance. So I found the midpoint between these 2 points, right? And that's what I did there. And then you have to find how far apart are the fountains this. So once you have the coordinates for each one, fountain one, that's one, and fountain two, that's the point. Then you're going to find the distance so you can find, apply distance formula so you can find what the distance is between the two fountains. The other application problem is actually, they can tell you, is this a isosceles triangle? Or this is an equilateral triangle? Or is this a right triangle? So you can actually prove it by finding the distance between the two vertices that form that segment, right? So if you have a triangle, and that triangle has A, B, C, right? And then you're trying to find the segment of AB, the segment of BC, and the segment of AC. And then, for example, here I'm trying to prove the isosceles, so I need to have two of the sides need to be equal. So we are going to see here that you have 3 square root of 5 and 3 square root of 5. So obviously, this triangle is isosceles, okay? So you're going to say, like with the proving method, we are going to say that BC is congruent to AC, then triangle ABC is isosceles triangle. And then remember that if you're simplifying, right, we got square root of 45. If you want an exact answer, we're still going to leave it with a root. So you're basically going to split the radicand, that's what this is called, between two factors, where one of the factors is a perfect square. And then we can take it out of the radical. And the next problem is really complicated. So I'm just going to give you the answers just in case you want to practice it. And if you want to take pictures, that's fine, or write it down, that's fine too. You can pause. And then we have circles, okay? So like I said, circles is going to have a center. That's your center. We're going to call it C. That center obviously is located on a point in X and a point in Y. But instead of writing X and Y, they write H and K. So, and H represents your X values and Y represents your Y values. And then this point right here on the circle, that point we're going to call XY. Now, I'm probably going to ask you to write the formula in standard form of a circle. The standard form of a circle with radius R and center HK is going to look like this, okay? So, and what does this look like? This looks like the distance formula because that's exactly what you're doing. You're finding the distance between these 2 points. So you have the change in the x's, square it, plus the change in the y's, square it, equals to the radius squared. So you know that if you want to find what the length is, then you're going to have to find the square root of that, right? Just like here. And then the general form is that you have the x's and the y's and the constant on one side, and then just equal to 0 on the other side, okay? So again, and here you needed to identify the center and identify the radius. So once again, the formula is with subtraction. So anywhere inside the parentheses that you have an addition, that tells me right away that these numbers are negative. So for example, on this one on D, I know that since I have a negative, I have a plus sign with the x's, that's going to be negative 11. And since I have a plus sign with the y, that's going to be a negative 6. Okay. And then from there, that gives you the center. And then you're going to take whatever, remember the r is squared, right? So whatever this side is, you're going to find the square root of that. And that one gave me what? 18? Okay. So let me give you the answers for this one. Again, you should pause it beforehand and then just work the problem, and then you can look in here. See, I was trying to model this one, what is happening, so you're aware of it. Okay. Then you can actually go backwards. I can give you the center and I can give you the radius, and then you need to write the equation in standard form. So again, since I had a negative with a minus, that turns into a positive. Remember, it's x minus h squared plus y minus k squared equals to r squared. So basically, that's what we're doing. We're substituting the x for the h and the y for the k. Okay, so this is h, k, and this is r. Okay, so again, check your work. Okay, and then one of the applications that you can do is that you want to, let me see here. You want to have, let me find the page. You want them to approximate what is pi, right? That we use so much and we don't know what it is. So how the pi came to be pi. So what we're going to do is that we are going to, you can bring to your students any round things. So you can bring like a round lids. I have a bunch of lids. That's what I did. I started collecting lids. I collected lids from my coffees. I collected lids from even the little water flavor things that has a little, I take those. Anything that has a lid that will not cut the students, you can do. As a matter of fact, since I wanted for students to have the same type of measurement, I gave you 5 back here. So this is what you're going to do. You're going to take a piece of string. Okay. Let me just put it right there. And any will do. See, this right here is the cable for my document camera. So you take a piece of string. Obviously, it's going to have a beginning and the end. And then you are going to measure around. Right? You're going to put it around. And try to use something that does not stretch too much. Because if it stretches too much, then you're not going to get the right answer. See right here? And then you're going to take the ruler. And I think I say use centimeters. You're going to take the ruler. And then you are going to, see, after you have marked it, you're going to measure. And that one gave me, what, 17? Maybe 17 and a half. And then I measure and then you record it. And then you're going to measure again the diameter, right? And then you're going to put in the diameter. So Miss Escobar, can I not just measure the diameter with the thing? Yes, you can. Right, and that's 5. Right, so the diameter is 5. And then, let's see. Yeah, 5. And then from there, then you're going to try to the, approximate the pi. So on the front, move the cable out. On the front, you have a little table to record your data according to those on the back, okay? So, uh, let's see. So that was number 3, I think. We had a diameter of 5, and the circumference, I think I said it was 17, around 17. And then we're going to divide it by 5, and we're going to get approximately 3.4, okay? Now, you're going to say, Ms. Escobar, that is not pi. No, it's not, okay? But it's very close to it. Remember I told you the pi is an approximation? So this is what I got. I don't know, I measure it again and measure difference, but this is what I got. So 2 is like pretty cool. It's like exactly 3.14. 5, I got 3.13. And see, in 6, when I did it, I got something different. So I don't know if it was my ruler or what it was, but I think I was using centimeters. Actually, I lied. I say millimeters in here. And what I was just using, it was centimeters. So you want to be able to measure those with millimeters and then divide it, and that's going to give you the approximation of pi. So in other words, taking the circumference and divide it by the diameter of the circle, that's going to give you an approximation of pi. Okay, so you can go ahead and write it down. And, okay, and then we have three-dimensional explorations. Now, please be aware that I will require you to use correct vocabulary and to be able to find surface area and be able to find um, total surface area, lateral surface area, volume. I'm going to ask you to be able to find those. Not only that, I'm also going to be able you to classify each one of these figures. Now, please be aware that when you are looking at the TEKS, like if you're trying to do already your final presentation, if you select kindergarten, all grades go through very similar naming, right? For example, they say, oh, you need to touch on volume. But the volume that you explain in kindergarten is not the volume that you explain in third grade or even in fifth grade or even in high school. It's more vocabulary elevated as you move along the grade levels. So, for example, something referring to volume in a kindergarten class will be to show them a glass, a clear glass, and as is the glass full? Is the glass half full? If the glass is almost empty, that is giving the student the reasoning of what is volume. When you say the word volume, what does that refer to? That refers to the quantity inside the object, the 3D object, right? Because it has an inside and has an outside. So in the inside, the quantity that is in the inside, that is what volume is referred to. So vocabulary, volume. But we don't talk about surface area. We don't talk about, uh, you know, all the other formulas. We're not going to talk about that in elementary classrooms. Okay, so depending on the grade level, the level of vocabulary and the level of difficulty of what you're doing is going to increase, right? So in here, we start with simple closed surfaces. Remember how we did in the previous chapter? Simple closed figures, right? Polygons, or simple figures, or closed figures. So these are going to be surfaces because we have 3 dimension, okay? So, and we have figures 1, we have all of these, figures 2, we got these 3. So, and you needed to say which one of these are simple closed surfaces. So if you remember, it still apply, right? Single surfaces means that they don't cross each other, right? So, and they don't have a hole. And closed means that they actually close. They start and end in the same place. That was for the polygons, or for the figures of the 2D figures. But the 3D figures, that kind of um, amplifies a little bigger, okay? So it says, what features will you distinguish between the simple closed surfaces, which are the first one, and the other figures, figure 2 are not? So what do they have in common? So this one has a hole. This one crosses in there, has actually 2 different areas, not one area. And this donut also have a hole, right? So that's what we're going to write down. We're going to write down simple closed figures do not have holes or have 2 different interiors, right? Like this one has 2 different interiors and these 2 have holes. So that's why all the figures 1 are simple closed surfaces. Then we're going to do part 2. So now out of that description that we already described simple closed surfaces, what are what we call polyhedron, okay? So polyhedron, as you see, poly means many, hedron means the 3D surface, okay? So let's take a look at what it says on the back. The back says, so take a look at figures 3 and take a look at figures 4. So you see that from here to here, we transfer these 2 down here. See? We have the slanted cylinder and we have the sphere. So it says, so figure 3 are polyhedrons. Okay, so all of these are polyhedrons. And then figure 4 are not. So these are not polyhedrons. Why? What features? Polyhedrons are made of polygons. Take a look. See? What are the faces of this? This is a pentagon and that's a rectangle. That's a pentagon and these are triangles. That's all squares and this is rectangles, rectangles. Actually, this is a parallelogram, 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 right? These are parallelograms. So they're made of rectangles, triangles, pentagons, so polygons. So they're made of different polygons. So polyhedrons are made of polygons. And then we have part 3, are pyramids. So what do you notice about these figures? They have only one base. See, this is the base. This is the base. This is the base. This is the base. And we name the pyramids by their bases. Okay, so it has only one base and all the sides are triangles. See, triangle, 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 triangle. All the triangles join in one vertex right here on the top. and that vertex is called apex. Okay, that vertex is called apex. So write that down. And then these right here are prism. So yes, let me tell you that in third grade, they do need to recognize what is the difference between a pyramid and what is the difference between a prism. They do need to recognize that. So a prism, what do you notice? They have a top and the bottom, and the top and the bottom are exactly the same. See, top and the bottom exactly the same, top and bottom exactly the same. What else do you notice? That's a rectangle, that's a rectangle, that's a parallelogram, and that's a rectangle, right? So we are going to say that the difference or the prisms are two congruent bases, right? They're always going to have two bases compared to the pyramid that they only have one base. And the sides are quadrilaterals that are parallelograms. And when I say parallelogram means you can have rectangles, squares, and rhombuses as well as the side. Now these nets, I actually went ahead and um I didn't have the I did not want it to color the color ones, so I just made a copy for it, and then that's what I use for these. But you have these right here in page, like I said, they're 211, 215. So you can cut them out and use them. Let's see, I don't think I have all of them in here. Let's see, so I have this one, which is not here yet. It's on the next page. I have this one. I have this one. I have this one, which is, I guess, on the next page. I have this one as well. And I have this one, okay? Now, these are going to be used for the next activity. It's going to be used for this activity right here, okay? And these what we call are nets, okay? That means that if you have a 3D polygon, let me show you this one. So first notice, they're all made of squares, right? And you see that you have 6 squares. So what type of figure are you going to be able to form? I'm going to be able to form a cube, right? Now, is this the only way to open it? No. And this is when your imagination, right, and how you cut it out so it will actually, they're all together. So they all need to be joined by at least one side. And then you're able to open it and see a cube, okay? So here you needed to match. These are from figure 7, come from figures 5 and 6, come from these two right here. So what do you think number 1 is? So number 1 is actually figure H. See, it has 2 triangles and then 3 rectangles. So that's a rectangular prism. Figure 2, I say is A. Why? Because it has only one vertex, see? And all the sides are triangles. So it's definitely a pyramid. In this one, you see that all the sides are triangle except for that big pentagon or hexagon because that's a pyramid again. See, and then that means that has a 1, 2, 3, 4, 5, 6. So that is just like what is it? 3 is D. Where's D? D right here. See a hexagon. And then we have see we got 2 of the same. That's a pentagon base, and you have 2 of them. And then all the sides are rectangles, so that's definitely going to be a prism. Okay, so for the next page, see? So again, you can play with this one and select all the ones that you think, okay, if I move this around, would this still be look like? How would it look like? How would you open it? So you need to be able to check each one of those with those cutouts that you have on the back, on those nets that you have on the back, okay? So I'm gonna give you again the answer for these, but again, pause, and then you can go ahead and um, and then check your answers. Now, one thing to be aware, nets need to be joined by an edge and not just by the vertex. So you cannot just say, oh, these 2 little ones are going to be a net. No, they have to be joined. See, like this, that is joined just by a vertex. That is not it. See, that's why that's a no. Okay. And then simply some of them don't work, right? Because where is going to be the triangle that goes on the bottom for this rectangular prism? I can't. So one of these has to be on the bottom to be able to be a rectangular prism. So you see that you can determine, see, this one is a no if you're going from here to here, right? Because if you fold this one, that's going to have a top, but this is also going to be on top of that one. So you're going to see that they don't close, they're overlapping. So let me show you the whole thing. Just make sure nets need to join by an edge, not by just a vertex. And let me try to make this a line a little bigger. Here you go. I'm going to show you that part. And I promise we're almost done for this chapter. I know it's a long chapter and it has a lot of information, but we're almost there, okay? These are things that you can check if you don't have it in your foldable and you can put it in, okay? Then on the back, And these are things that students do need to learn early. And actually, you can do it like in kindergarten. And the way that teachers present this is like using, for example, you can use, if you want to bring food into the classroom, because that is an iffy question, but you can bring pretzel sticks and little marshmallows, and the students can form the 3D figures, the basic 3D figures that is defined in the TEKS. And they need to say how many faces, how many edges, and how many vertices. And it's important that you use the correct vocabulary so the students is consistent through the years of naming the correct vocabulary. Okay. Um, and you're going to see that after we explore, because this is kind of like an exploration activity, after you explore figure 5 and figure 6, you explore the number of sides, edges, and vertices. You're going to try to name the figure. Remember, I told you the pyramids are named by their bases, just like the prisms, right? So the prism just have two of them, but the pyramid just have one. But they're still named by their bases. And then you need to notice between the faces and the vertices, right? So, and you're going to find out Euler's formula. Euler's formula says that when you add the faces and the vertices, that's going to be equal to the edges plus 2. Or if you add the vertices and the faces and subtract 2, that's going to be the edges. It's the same formula. It's just one solved for E and the other one is not solved for E. Okay. So, and I think on the homework, which I don't know where I put now, you do have something like that too. I don't know where I put the homework. I'm really trying to know. Um, let me see. Nope. But yeah, I know I have it somewhere, but oh, yeah, I found it. Hold on. Let's see. Um, See, this one was using the distance formula, which is similar to what I show you. This is using the Pythagorean, showing you the half isosceles. This is just like the example that I just showed you in the classwork. Um, Name the solid, write Euler's formula, use Euler's formula to find what you're missing. You need to show me, you need to write the formula, substitute, solve like the equation, and then show me whatever it is that you're missing. And then see which one of this, which polyhedron does not belong to this net. So which one of these belong? So which one of this belongs to this net? So you need to select the one that goes along with this one. Again, all of these problems you have in your workbook. So because I got it from there. The only thing that is not in your workbook is number 2, and number 2 comes from discussion 2. So you must do discussion 2 before you can actually answer this. And this problem is coming on the test on the final exam as well. So so just FYI, okay? Because partial 2 is just 3 and 4, and then 5 and 6 is just added to the final. So just FYI. Okay. Now we're going to look into surface area. And I think there was something on the bottom. Yeah, so on the bottom on page 166, we got what we call the total surface area. That is basically, think of the metal used to make the can of soup. They have their cylinders, right? And then they have the top and the bottom, they're circles. And then the whole surrounded of this are going to be a rectangle. So if I made a net for a can, it will look something like this. See top and bottom? And then the rectangle, that is the label part or whatever the part is, right? So if I find the area of the two circles and add it to the area of the rectangle, that's going to be giving me the total surface area. But if I only find the area of the label, that is going to give me the lateral surface area, okay? So the total includes the top and the bottom. The lateral only includes the side, okay? So having said that, so all of these, I will give you the formula. You do not need to memorize the formula for surface area or lateral surface area or, or volume. All of those, I am going to give it to you. The only thing I ask is that you know how to use them, right? So you know how to substitute correctly or when you're missing information and what are you going to do about it, okay? So I am just, for this part, I'm just going to give you a chance to write down or, let me see, I'm trying to see if I can. I cannot show you all of it at one time. So let me just show you this, and then I can show you 6 in a minute because I also did some work on the bottom. So in here, right, I did the net, I find the different rectangles, and I did the triangles. Remember, these two triangles are congruent because that's a prism, not a pyramid. And then you can add the lateral surface areas, it's like the blue area, and the total surface area is going to be the blue area plus the triangles, right? And this pyramid, you have the apothegm, right, which is the height of the triangle. Once you find that, you're able to add all those together or multiply by the number of triangles, which is what I did here. And then if you need to add the area of the square, then you add the area of the square. And then on the bottom, it's not as easy, right? So you have this triangle right here, or very similar to this triangle. See right here? And then we're going to say that that was 15 and 8, and you needed to find the lateral side right here. So yeah, so there was additional work that we had to do in round to be able to get to where we wanted. Okay. And we have the back, the cylinder, and we have a pentagonal prism. And then the last part, I'm going to put in the bottom in here. This is what I did to calculate this right here. And then the last part, all this is about area. So the next thing that we're going to look is volume. Okay. So, and we may do a relationship first of surface area and volume and how they vary according to the length. And for that, you can basically use any connector cube, right? Just like the ones we have used in the classroom, the connector cubes, right? And the student can form an arrangement, and then you can tell them, okay, find the surface area, which is everything, including the bottom, everything that will cover this. If you want to wrap it with wrapping paper, right? What is all the different unit squares? And these little ones are unit squares, right? So we have for that, we got the front, we got 1, 2, 3, 4, 5, 6. That's the front, the one that you see. Then we have the back, which is 1, 2, 3, 4, 5, 6 as well. Then we got the right side, so it's like swing from here. 1, 2, 3, 4, 5. Then we got the left side. 1, 2, 3, 4, 5. And then we got the top, which is 1, 2, 3, 4, 5, 6, 7. And then the bottom, we got 1, 2, 3, 4, 5, 6, 7. So we counted all of them and got 36 unit squares. Okay. But the volume, right? The volume will be what? It will be the number of squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You got 10 cubes. So each one is going to be 1 cubic unit. So that means you have 10 cubic units. So now we're going to use cube instead of square because we're talking about the 3D. And if you see by just separating this over here, right? So we are going to see that we are exposing whatever this was hiding, right? We are exposing it. But you're still going to see what? You're still going to see 36 units squared, but the volume changed a little bit. Because you see also this one is also missing this one right here. That one is also missing that one. Okay, so we not only separated this one from here, we also deleted these right here. Okay, so we're going to say the volume is different, but the surface area is the same. And then we have 36 unit squares. It's using the same number of blocks in figure 1. Make a different configuration than the one that is given you. So basically I had 1, 2, 3, 4, 5, 6, 7, 8 on the bottom, and then a tower of 2. So in other words, I put this one down here. That's what I put the pink one down here. So I have 2, 3, 4, 5, 6, 7, 8, and then these two just stack on top. And I still have the same volume and the same surface area. Okay. So again, you do not need to memorize the formula. I will give you the formula. You just need to know how to use it, how to get the information from the figure that I'm giving you. Okay, so how to give you that information. And again, you can pause it, work the problem out. And as you see, when you have pyramids, you may have to use Pythagorean theorem to be able to get the height. And when you are comparing ratios, that's the next one on page 171, right? So you need to remember linear measurements, the scale factor is K, okay? So you have centimeters, inches, meters, whatever. It's just a unit. When you are finding area, what happened to those units? That unit squares, right? So we went from a scale of K to a scale of K squared, okay? And when you're talking about volumes, then that's going to be K cubed, okay? So look at this. So you have two rectangles, one with a diagonal of 25, the other with a diagonal of 35. Assume that the rectangles are similar. That means they have congruent angles, but the sides have the same ratio. Then the ratio of the big rectangle, which is 35 inches, to the small rectangle, which is 25 inches in diagonal, will be 35 over 25. And we squared to find the area, which is 35 divided by 25 squared, which is 1.96. Okay, which is approximately around 2. It says the statement is correct, right? According to what it says, it's twice the viewing area. And the 35 inches is twice the area of the 25 inches, right? So basically, you're using math to justify your point in regarding to how much TV area you can see. Okay, so let me show you the other two. And I'm going to show you B and C. And then remember how we did this before? So that we did this tables of conversions at the beginning. I think it was chapter 2. Now we're going to do it, but with areas and cubes. So if we knew that 1 foot is equal to 12 inches, then if you need to find inches cube, then you're going to represent it 3 times. See, inches times inches times inches is inches cubed. And then we're converting that into feet cube. So let me show you in here the answers for that bottom part. And then I'm going to show you the answers for the next page. Next page. And then from there on, you just have like a summary. And in the summary, it's like I gather all the different formulas in all the different tables, and I just put it in one place, okay? Now, there's one typo. It's on page 174 when it says mass, and it should say 0.001 kilograms. Because right now it's blank. And then the other one that you have is the gallon man. There are different versions of the gallon man. But basically, it tells the student the different ways in which you can form a gallon. The first one is that a gallon is 4 quarts. See? A gallon is 4 quarts. What is a gallon? A gallon is 1, 2, 3, 4, 5, 6, 7, 8 pints. And a gallon is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 cups. And all that is equal to 1 gallon. So this is kind of a cool thing to remember. Just make sure you tell your students that it's just 4 fingers and not 5, right? When you're doing this type of activity. And like I said, the rest of it is just summary, summary, summary. The only thing that we did not went over, and it's on page 181, is what they call the Cavalier principle. And the Cavalier principle says that if you have a stack of coins or a stack of paper or a stack of books, right? They may be straight like that, but then somebody pushed it and kind of slide it a little bit, right? Still, you see kind of following the pattern, right? Even like here, this is crazy. These two figures, even though they don't look anything the same, they're going to have the same volume, okay? Have equal volumes. So that's what they call the Cavalier principle because they have equal volumes, okay? Okay, guys, I think this has been a very, very, very long video. But like I said, this is kind of 2 class periods of class, okay? Because it is chapter 6 is dense. So, and then the only thing that we have left will be to go over chapter 5. And that one I would prefer to do it virtually, okay? I mean, personally. So we're going to see it in